we now want to put all the ideas we've learned about calculus and curve sketching into a set problem. So the idea is use the ideas of the first derivative and second derivative to draw a curve that we're given. So our curve we're given in this first case is 3x minus x cubed, and we've got to do a few things with it. So first one, we want to show that it represents an odd function. Well, how do we do that? Well, we know if we substitute minus x in, that we're able to sub it in and then manipulate our algebra. So we get minus 3x plus x cubed, which we can then factorize a negative out, and we get the negative outside the function itself, which means that that's an odd function. We know if we can go from this point and get down to here, then that must be an odd function. So that's going to help us draw it up because we know we have point symmetry. So the second part, find all the stationary points in their nature. Well, to find our stationary points, we get our first derivative and we set it equal to 0. So our first derivative, 3 minus x, 3x squared, set it equal to 0, factorize, and from this we get our y value, x values of x minus 1 and 1 from our brackets. And we know that we can get when x is equal to 1, our y value would be equal to 2. And we're using the second derivative to test. So our second derivative would be, we haven't actually got it there, but our second derivative, let's just write down our second derivative, would be minus 6x. So we substitute 1 into that, we get negative 6, which means it's concave down, which means that 1, 2 must be a maximum. And if we didn't do it for minus 1, but we put minus 1 in, that would mean we'd get our y value at minus 2. So when x is equal to minus 1, y would equal minus 2. And we get our second derivative at minus 1 would be minus 6 times minus 1, which would give us a positive 6. So that means our second derivative is positive, so it's concave up. So the point minus 1 minus 2 would be a minimum. So that's our two stationary points in their nature. Any points of inflection? Well, again, we said our first derivative was minus 6x. We set it equal to 0. When x is equal to 0, y would be equal to 0. We check for our concavity change. So we put 0 in. We check at minus 1. We saw that was positive, and at 1 we saw it was negative. So there is a change in concavity. So the curve was concave up, then becomes 0, and then it's concave down. So as there's a change in sign, there's a change in concavity, and we must have a point of inflection. Remember, we always have to test that. Sketch the curve for minus 2 to 2.5. So there's our curve there. We make sure we're drawing it up with our stationary points there, as well as our endpoints, because we've got a set domain here. We have to get the values of minus 2 and 2, and it looks like it's 2.5, about minus 8. So make sure you get those those values right there, and then we can, from our graph here, we can look and go, well, what would be the maximum minimum values of the curve in this domain? Well, we can see that we're getting a value here and the value here. So the maximum value would be 2. The minimum value is minus 8 and 1/8, or minus 8.125. Because we can see when it's 2.5, that's the value we get. So in our next problem, we're doing the same, similar. We get our first derivative. We want to get our turning points and determine their nature. We get our first derivative, set it equal to 0. We're using the second derivative again because it's not too bad to use. And so when x is equal to minus 3, we get our y value of minus 28. And the second derivative is positive, so it must be negative, it must be a maximum. And when x is equal to minus 1, y would be minus 4. So again, we're just subbing it into the equation. And our second derivative is positive, so it must be a minimum because it must be concave up at that point. So find any points of inflection. So we get our second derivative, set it equal to 0. So we've got a possible point of inflection at minus 1. And we see that when we sub our values in either side, we get minus 2, which is negative, and 0, which is positive. And so we get a change in sign for our concavity, so that must be a point of inflection. Where does the graph cut the y-axis? Well, we know when x is equal to 0, We get y is equal to 1. That's not too bad. So we got our y-intercept. Now sketch the curve showing those features. So we got our we got our stationary points there. We got our point of inflection, which we'll just go back and check, which was at -1. We thought it was -1. So we got our point of inflection there. And then find the set of values for which the curve is increasing. Well, again, what do we mean by increasing? We mean the first derivative is greater than 0. So where's that curve greater than 0? Again, we can go back and look on our graph. We know it's increasing here, and we increase there. So we can do that pretty easily. And then find the values of x which the curve is concave up. Well, we know it's concave up from -1 onwards. So it's pretty easy to read off our graph. Analytically, we can solve it that way with the algebra, but we can do it with our graph as well. So we don't really need to have this or this part, but that's fine if you want to solve it analytically or geometrically by just reading it off the graph.